In this lecture, we're going to discuss a third and final matrix factorization technique from a few different perspectives, but they all relate to something called principal component analysis. So principal component analysis is often used for something called dimensionality reduction. And here's a slide that's going to make that a bit more intuitive. Imagine we're given data x1 through xn, where each point is in Rd, where we're going to assume that D is very high dimensional. However, we don't think that the information fills all of those dimensions. We think that we can take all the information contained in that high dimensional space and map it to a much lower dimensional space where we don't lose much information. In this case, meaning that the vectors in the lower dimensional space all kind of have the same relationship to each other that they had in the higher dimensional space. And so learning an algorithm on data from the lower dimensional space shouldn't give worse results than what we would get from learning on a higher dimensional space. Here's an example of that where we have high dimensional images. So if we view this as each image as a point in a very high dimensional space, we would have these five different points all in the same space. However, instead of having to represent it in that image space, if you notice that these 5 images all really can be captured by 3 numbers, since all we need to do is learn a shift and learn a rotation, 2 shifts and 1 rotation for these 3 images. So where's the center? That's a 2-dimensional vector for the center of the 3, and then the rotation is a 3rd dimension. And so really we only need 3 numbers for this data set to capture everything going into it. And then we just also need the base pattern of a 3 that's going to be reappearing in each of these images. So this is an extreme example, but also actually very relevant to many data sets. So principal component analysis can be thought of as a way for automatically learning a mapping from this high dimensional space to a low dimensional space such that we capture all of the information from the high dimensional space. To discuss principal component analysis, it helps to think of a toy example. So how can we take this data set of these points in 2-dimensional space? So each point, for example, xi is represented by 2 numbers that gives this point here. And we want to take a vector q of unit length and represent each of these points in terms of the vector q. So PCA essentially does this problem. It says, take this vector q, make it unit length, and now represent each of these data points by dropping a line perpendicular to the line constructed by the direction of q. So this arrow q defines this line here. And now we're going to take each of these points and drop it to that point there, perpendicular to q. Now we want to take each of these points and represent it by the amount that we have to stretch q to get to the red dot by dropping that line. So for example, we're going to take this 2-dimensional vector and represent it by 1 number. It's the number that we have to multiply q by to get it to stretch out to this red dot here, which is the closest we can take q and get it to the point xi. So we've already discussed some of these geometric concepts in the classification portion of our course, where we talked about linearly separating hyperplanes and dot products. In this case, that shows itself by taking the dot product between q and each point xi. And now if we wanted to know what does this dot product of this unit vector q with xi represent, that represents the length from this origin to the red dot here. So if we want to know what's the length from the origin to the red dot that I get by dropping this point x perpendicular to this line here defined by q, that length is equal to q transpose times xi. Therefore, if I want to take the vector q and I want to stretch it so that I hit this red point here, which is the closest I can take q and get it to xi, I simply want to take q and multiply it by the scalar that I get from q transpose xi. So this is the amount that I have to multiply q by to stretch it out to get it to hit that red point. And now in that sense, so this is a very simple toy example that doesn't do justice to what PCA is used for, but we can visualize it. In that sense, what we've done is we've taken each of these two-dimensional points, which each requires two numbers to represent it, and we've reduced each point to requiring only one number to represent it. And that's the number that I need to multiply q by to stretch it out to get as close as possible to xi. So I've done a very trivial and not interesting example of dimensionality reduction by taking a two-dimensional vector and reducing it now to one dimension. And so for each of these points, I need to keep only one number. I need to keep the value of q transpose xi. And then also somewhere I need to keep the vector q, potentially, if I want to construct this, try to reconstruct this space. So this, as simple as it seems, and as potentially uninteresting given this plot as it seems, this is the basis for PCA, and it's very important and very useful. And so now the question naturally becomes, if I only get one vector q that has to be unit length in order to do this, what's the best q to pick? What's the best vector? So I picked a good one here that kind of is cutting through the data nicely. I could have picked another vector q and pointed it in this direction, and maybe that would have given a completely different result. So which is the best vector q to pick for a problem like this? And so to do this, we again have to set up an objective function, some measure of quality that we can then, a mathematical measure of quality that we can then minimize to say we found the best vector q according to this measure of quality. And so the way that we do this, which is no surprise, is the squared error. So we take the squared error term of this approximation. So we have a vector xi, and now we approximate that as with the vector q stretched out by the product q transpose xi. So we take q transpose, multiply it by xi. That's the amount that we now stretch out q. And this is now our approximation in the same dimensional space as xi. And so we approximate xi with this. And so that's all this is showing. We're taking this two-dimensional vector and approximating it with this two-dimensional vector. But all of those approximations have to fall along the same one-dimensional subspace. We square that error and now sum the squared errors, and we now try to find the minimum value of the vector q to minimize this sum of squared errors, subject to q having to be unit length. So this is the PCA problem in a nutshell. However, we're going to simplify it, or we're going to rewrite it in a different way, in a different equivalent way, which is how it can be done in a computer. So we want to minimize this. We want to find a vector q, and so now in your mind you can imagine that this is much higher dimensional. X could be thousands of dimensions, and q therefore is a 1,000-dimensional vector that has unit length. And now we want to find that individual single high-dimensional vector to approximate the vector xi. And so again, we take that vector, we take the dot product of it with xi. That's the amount that we have to stretch that vector in order to get it as close as possible to xi. So this is our approximation. This is our error. We square the error and sum it up, subject to q having to be unit length. But now instead of writing it this way, let's expand this product out. So we multiply this whole thing out. So remember, this is a vector, and if we want to know the squared magnitude of that vector, we can simply take the vector transpose multiplied by itself. And so when we do that, we get an x transpose x, which is this term here. And when we multiply this thing by itself, what we get is a q. We get some q's that cancel out with each other. And when we multiply these things together, we also get some things to cancel out with each other. So the cross term of this, as well as this term with itself, gives this product right here. So this is an equivalent way to write it. And so I've simplified this by taking the sum and bringing it in here. And now we want to find the argmin of this term minus this term. And so now, instead of summing the outer products of each of these points xi, let's view this as a matrix product for simplicity. So in the first half of this course, we viewed each of these xi's as being put on a row of a matrix X. Now we're going to switch that, and we're going to say, take each vector xi and put it in a column of a matrix X. So the matrix capital X is constructed by taking each of our data points xi and putting it along a column. And so it's d by n. And now this product is equal to x times x transpose in that sense. So now we want to minimize this term, which is exactly the same as this term, but written in a different way, and also using matrix products here. However, if you notice, this term doesn't include q at all, so we can simply throw it away. And if we want to minimize a negative term, we also want to maximize the negative of that term. So we want to maximize this term in q. And so an equivalent, a mathematically identical way to represent this problem is finding the vector q that maximizes this quadratic term subject to the magnitude of q equaling 1. So we want to take q transpose times the matrix that we get by taking this matrix product times q, and we want to now find the vector q that maximizes that product. This vector q has a name. It's called the first eigenvector of the matrix XX transpose. Notice that this thing is d by d and symmetric. And the value of this product, evaluated at the optimal q, is called the first eigenvalue. So if we take q transpose times this matrix times q, the value of the maximum, that's the maximum value we can get by that type of a product subject to this constraint. Call that lambda. That's the first eigenvalue.